This type of question is fairly common on Maths Olympiads and some of the more complicated college entrance tests. We have a Diophantine equation and they want us to count how many triples of integers satisfy this equation here. Okay, now counting is a lot more difficult than just 1 plus 2 plus 3 and all that sort of stuff. Sometimes it gets very complicated, so we have to be very careful. Now, clearly what we can't do is just put random x, y and z in and hope that they add up to 181. What we need to do is we need to get rid of this rather unwieldy expression and factorise it somehow so that we can have a method for solving this. Now, because there's x, y, z here, we know that we should be doing something along the lines of factorising it like thus. And because there's x, y, y, z and x, z, we can be pretty sure that it's wanting us to factorise like this. Now, if we expand x plus 1, y plus 1, z plus 1, we get x, y, z, add x, y, add x, z, add y, z, add x, add y, add z, add 1. Okay, so basically this expression here is equal to x plus 1, y plus 1, z plus 1 minus 1. So we can rewrite the expression that we want as x plus 1, y plus 1, z plus 1 minus 1 equals 181, i.e. they want us to find the triples which satisfy this equation, which is far easier because now we can use a method. Now, the number 182 is actually a sphenic number, which is very convenient because what it means is it is the product of 3 primes. And you'll often find in these sort of equations and questions that this number here will either be a prime or a semi-prime or a product of primes, because otherwise there are so many solutions that it becomes almost impossible to count. So 182 is, by basic prime factorization method, 2 times 7 times 13. So we know that basically x plus 1, y plus 1 and z plus 1 are going to be some sort of combinations of this, so we can begin to count. Now, to start with, let's just deal with the positive integers, and then we'll deal with the negative integers once we've worked out precisely how many positive triples there are. So let's just have maybe do a little bit of a table. X plus 1, y plus 1, z plus 1. And remember, we're not dealing with x, y and z, we're dealing with x plus 1, y plus 1 and z plus 1, and we know that they have to multiply together to be 182. Well, clearly, one solution is 2, 7 and 13, because we know that 2 times 7 times 13 is 182. So there's solution number 1. And we can permutate this because x, y and z are no specifics, so we know that also we have 2, 13, 7, we have 7, 2, 13, 7, 13, 2, 13, 2, 7 and 13, 7, 2. So basically there are 3 factorial perms there. So that's the easy bit started. But in actual fact, there are quite a few more, because we could have x plus 1 being 1, and therefore y plus 1 could be, for example, 2 times 7, and z plus 1 could be 13, and we can have 3 factorial permutations of that. It doesn't have to be x is 1, y is 14 and z is 13. We can permutate that around. But also we have 1, 2 times 13 and 7, and there are 3 factorial perms of that. And also we have 1, 7 times 13 and 2, and again there are 3 factorial permutations that I won't write them all out. By the way, at the end of this video I will do a complete list of all of the x, y, z for anybody who wants that list. So we know that we got 3 factorial here, and then doing combinations of 2 of the numbers we have another 3 lots of 3 factorial, which is 6, 6, 6 and 6, and then we also have the final one, which is 1, 1 and 2 times 7 times 13, and clearly there are going to be 3 of those. So if we add up all of these, we have 27 triples of x plus 1, y plus 1, z plus 1, where they are greater than or equal to 0 and where they equal 182. So we're halfway there. What about the negative numbers? Well, in actual fact, for negative numbers, it's fairly simple, because all we have to do is, let's look at any one solution. It doesn't matter which solution we look at. Let's look at this one, 2, 7 and 13. If 2 times 7 times 13 is 182, then we also know that minus 2 times minus 7 times 13 is 182. And we also know that minus 2 times 7 times minus 13 is 182. And we also know that 2 times minus 7 times minus 13 is 182. So for every positive solution, we know that there are 3 other solutions basically involving the various combinations of putting 2 minuses out of 3. So in actual fact, the total number of triples, and that's what they're asking in the question, how many triples of integers x, y, and z satisfy this? The total number is equal to 27 times 4, which is the 27 positives, and for each of those 27 positives, there are 3 which involve 2 negative numbers. So the total number of triples is 108. Now, for those so interested, we actually just have here a list of all of the triples. So I'm not 100% sure how to do this, so let's just put them there. So here is just counting them. Here's the x value, the y value, and the z value. Here is x plus 1 times y plus 1 times z plus 1, and here is the actual question, which was x, y, z, add x, y, add y, z, add x, z, add x, add y, add z equals 181. So here's number 1 to 30. You can pause the video if you actually want to see them. And then number 31 to 60 is that one. Again, pause the video if you're so interested. And then 61 to 90 is here. And then the final ones are here, 91 to 108. Now just one other thing. In actual fact, the number 182 isn't particularly special. Well, it is special in that it's sphenic, but there are an infinite number of sphenic numbers. Any equation like this, where that is a sphenic number, will have 108 triple of integer solutions, where an integer can be positive or negative, and it will have 27 integer solutions, triples, where the integers have to be 0 or greater than or equal to 0. And given that this is a fairly common question, that's quite a useful little snippet to know. Okay, well, I hope you enjoyed this. Please subscribe to the Gresty Academy YouTube channel if you're so interested. Thank you.